All right, my friends, welcome back. We're going to spend the first little bit talking about cyclohexane conformations, and we'll move on to stereochemistry. Just a reminder of where we are. We have an exam planned for next week. I know that's really fast after this previous exam, but that's the problem in a spring semester. Later today, I will email all of you who have taken the exam a link to a video that will explain the right answers to all the questions. You should be able to see your responses and items missed on the Testing Center website, and then you can see sort of what you did wrong. The best thing you can do to prepare for the next exam is to find out precisely those things that you struggle with, that you're weak on, and then practice them. To that end, study guides for chapters 4 was already up, 5 and 6 and 7 and 8 are already up. There is almost zero chance we're going to get to chapters 7 and 8 by the exam. I will write the exam to test only on the things that we've covered. So we'll have to be a little bit flexible with the plan. The practice exam is also up. That practice exam covers all the way through chapters 7 and 8. You only have to do right now the parts that are relevant. So feel free to, when the time comes, report that you've completed the practice exam, even though there will be some of it that we won't do until the next section. All right. So yes?
When are you going to post the answers?
To the practice exam? Did I not do that yet?
Oh, have you?
I haven't. I posted the practice exam, but not the answer key. Yeah, I will do that like now or today. Not right now, but. All right. So I wanted to just address a question that's come up a couple of times. Your text refers to this concept of strain when talking about conformations of organic molecules. One of the ways that it talks about strain is angle strain, and that's related to the fact that in some rings it is impossible to adopt the idealized 109.5 or whatever degree bond angle required for sp3 hybridized carbons. So that's what we mean by angle strain. And then the other kind of strain your text talks about is torsional strain, and I don't really make this distinction. Your text uses torsional strain only to describe the fact that staggered conformation is more stable than the eclipsed conformation. It uses the word sterics to talk about having groups gauche versus anti in a Newman projection to describe how this arrangement is less stable than this arrangement. Oops, I'm totally messing that up. But the origin of both of these effects, what am I doing? The origin of both of these effects is sterics, and sterics is just another way of saying electron-electron repulsion of large groups. Of course, I guess we had another explanation for staggered versus eclipsed, and that was hyperconjugation. But the reason I don't make a distinction between torsional strain and then sterics and gauche versus anti is because they derive from the same basic principles. So there may be a question that you had to do for the study guide was identify the elements of torsional strain versus other kinds of strain. And you should know what angle strain is, and you should be able to use sterics to rationalize the strain that's associated with rotation around carbon-carbon bonds. Because frankly, I think this is torsion refers to rotation around a bond, and this gauche versus anti issue is an issue of that too. So that may muddy the water just a little bit, and I'm sorry, but we're not going to make a distinction between these 2 points. Okay, so I just wanted to remind you that if we have a flat six-membered ring, the bond angles could be around 108. But if you looked at that ring from the side, what you would see is if it were perfectly flat, all the carbon-hydrogen bonds would be eclipsed with each other. In fact, if we looked in this sort of flat conformation, if we looked down this carbon-carbon bond, what we would see, ring is here, ring is there, all the carbon-hydrogen bonds in the front would be eclipsed, and all the with carbon-hydrogen bonds in the back. And so, if the ring is totally flat, you've got, even though you haven't got a lot of angle strain for the 5-membered ring, you do have this so-called torsional strain due to the eclipsed interactions. So to avoid that, as I showed you, the 5-membered ring is going to adopt what some people call an envelope conformation, so that at least for some of these carbon-hydrogen bonds, if we were to look down a carbon-carbon bond, we would see that at least for some of them, we've got a more staggered conformation than eclipsed. And I'm going to try to show you that that's the case using the Spartan app, where I've got a cyclopentane ring here. And you can see it's not perfectly flat. It's adopted this sort of envelope conformation where, see that okay? Do I need to, oh, we're already there. Envelope conformation where one of the carbons is sort of lower than the others. If we look down this carbon-carbon bond, let's see, gotta get my laser pointer. If we look down this one on the left, you can see it's not perfectly staggered, but it's not eclipsed. All right. There's the CHs in the front, there's the CHs in the back. So at least with some of these carbons, you're able to get some not fully eclipsed situations, though for others of them, it's pretty dang close to eclipsed. Okay? So a 5-membered ring is okay, but it does experience, it doesn't experience a whole lot of angle strain, but it does still experience some torsional strain. So now, anything we want to talk about there? Go ahead.
So is the only carbon ring that can't really like bend itself, is that the one in a triangle?
That's right. That is the only kind of ring that can't sort of pucker and relax the cyclopropane that's in a triangle. Yes, because 3 points define a plane. So what are you going to do? There's no way around it. Yeah. Okay. So now we're going to talk about why organic chemists love the 6-membered ring. And at first, if you draw a hexagon and if it's flat and all the sides are equal in length, then the bond angles have to be 120. So you might conclude, uh-oh, now we've gone past the ideal angle for sp3 hybridized carbons, and now we're even further, so that should be some angle strain the wrong way. And that would be true if the ring were flat. Again, if we drew the ring flat and sort of looked down a carbon-carbon bond, we would have the same problem that we listed above for the 5-membered ring if it were flat. We would have CH bonds on a carbon in the front eclipsed with CH bonds and a carbon in the back. So instead, that flat ring is going to pucker, but it's going to do so in an interesting way. And this is something that you're going to need to get good at drawing. I'll talk to you about how to do that in a little bit. In this puckered conformation, all of the bond angles are around 109 degrees. And then if we look down any of the carbon-carbon bonds, we will see a perfectly staggered situation. All right, here is the carbon in the front. And from our perspective, the proton would be coming out to our right, and the proton that's going down would be going down this way in the Newman projection. In the back, we would see a proton coming straight up, and another headed out to our right but angled downward. And so in the six-membered ring, you can get perfectly staggered carbon-hydrogen bonds, so there is no torsional strain or no steric strain associated with having things that are a little bit too close to eclipsed. Whereas in the five-membered ring, everything was not perfectly staggered. So to demonstrate that, let me show you again in Spartan the six-membered ring. Looks nice and flat. Whoa, how did that happen? Oh, okay. Looks flat from above, but if we zoom in and look at it, let's look down one of these carbon-hydrogen bonds. So just like we did in the drawing on the other slide, let's look down this carbon-hydrogen bond. Okay, and as we do so, we notice here's the carbon in the front. We got a proton that's down and a proton that's up. And then in the carbon in the back, we have a proton that's up and one that's down, but they are staggered with each other. And so there are, and this is true, unlike the five-membered ring, this is true sort of all the way around. So I'm just going to sort of slowly rotate and give you the Newman projection for each of these carbons. And as I do that, I want you to just convince yourself that we've got staggered conformations about all of the carbon-carbon bonds. Got it? All right. So in the six-membered ring, there's no more of this strain associated with the fact that staggered is more stable than eclipsed, because all of the carbon-carbon bonds have this staggered conformation. You'll notice some interesting features of this. Well, hold on. And I could tell you, like if we measured bond angles, you would see that the bond angles here are pretty near perfect for sp3 hybridized carbons. So for the six-membered ring, there isn't angle strain, and there also isn't the strain associated with sterics for rotation around carbon-carbon bonds. So the six-membered ring is a nice sort of environment. Six-membered rings are pretty easy to make in OChem, and it's the best, the most well understood ring system where we understand the most about the conformations of this six-membered ring. So this particular conformation has a name. It's called a chair, and in order to see it, you sort of have to look at it on the side, and then imagine that this is sort of an Adirondack chair where your head would go here, you're leaning here, and you sit there, and then your legs go there. It's not great, but the name stuck. I mean, honestly, your head would be bumping into this hydrogen, so you couldn't actually sit on it. So let's talk about the features of the chair. One of the things that you might notice as we look at this is that you have some carbon-hydrogen bonds that are pointing up or down, and you have others that are splayed out to the side. So we're going to describe here two different kinds of hydrogens. The ones that are angled upward, or rather sort of the ones that are vertical, we're going to call axial. So I'm not explaining this particularly well. Imagine that the carbon atoms of this ring are like a belt around a sphere. And you have protons above that are pointing towards the sort of north pole or aligned with the axis of the sphere. These are called up axial protons. Then you have protons down here that are pointing towards the south pole of the sphere. They are down and they are aligned with the axis of the sphere, so this would be down axial protons. In contrast, you have other protons that are splayed outward, sort of along the equator of our sphere, and so we call them equatorial protons. Here is an up equatorial proton because it's angled up towards the north pole, but it's equatorial. This is a down equatorial proton because it's angled towards the south pole, but is an equatorial proton. Okay. Do you see the distinction? All right. One other thing. If we look at this ring and imagine it as being sort of distorted from being perfectly flat, then we have carbons like this one right in the front that are sort of at an up position. The bonds leading to it are angled upward, so I'm going to call that an up carbon. And then you have other carbons like this one, which I'm going to rotate around so you can see it, where this carbon is sort of angled downward. The bonds that are connected to this carbon are angled downward in sort of a V. So I'm going to call this a down carbon. All right? Up carbons, down carbons. One of the things that is interesting is that up carbons have up axial protons and down carbons have down axial protons. All right, any questions you want to ask so far? Okay, so let me work through drawing this six-membered ring and some of the misconceptions that people get, all right?
All right, so how do we draw the chair conformation? How do we represent that on paper? So here you go. You start with a diagonal line that's angled down this way. And you didn't know this was art class, but it is. Now, I think we've been updated. That's different. I don't know if I like that. All right, you didn't know this was art class. You need to get good at drawing chairs. Now, obviously on my exams, you're not gonna be drawing anything because it's multiple choice, but being able to draw the chair and think about it will help you to get questions right on my multiple choice exams. So, to draw a chair, you angle a line downward, kind of like that, and then you draw another one some distance away, like that. And we're going to see that in a chair conformation, bonds that are opposite to each other across the ring are going to be parallel to each other. So I'm going to draw another line here, angled downward. Oops. And another line here across, angled downward. See where we're going? And now I just need to connect the lines. Isn't that nice? Okay. I don't have to draw it that way. I could angle my lines like this. I could also do this. That's kind of ugly. All right. So just so we're all on the same page, in blue, I'm going to highlight the up carbons. And let's use purple for the down carbons. And on the up carbons, now we're going to draw the substituents. On the up carbons, we're going to draw let's just do cyclohexane, a carbon-hydrogen bond pointing straight up towards the top of the page. And here's where you have to get a little sort of creative. If you want, you can even do this kind of thing to indicate that this bond here in the front is in front of the carbon bond in the back. That's fine. Now we're going to draw in the down axial substituents. And again, we start with the down carbons and angle things downward. Right? Okay. Now the tough part is often the equatorial substituents, and people struggle with this a little bit. The best thing I can say is that I want, let's see, the equatorial, I didn't want to erase that. The equatorial substituents are going to be parallel to bonds that are one bond away. Do you see how this equatorial hydrogen is parallel to this carbon-carbon bond and that one? So that's how you can follow where your equatorial hydrogen should point. The other thing you can do is to say, okay, this is an up carbon, and on an up carbon, the down substituent has to be equatorial. This is up axial. Let's see, sorry. That there. So on purple down carbon right here, the bonds I'm going to want to be parallel to are these. Right? And then on this blue up carbon, the down equatorial hydrogen, I'm running out of colors, needs to be parallel to these ones. So that's going to angle out towards you. We can do the same thing over here. And again, the one in the back is often difficult to draw. But again, notice that it's parallel to these two. All right. Classic mistakes in chair drawing that I see are, I'm just going to copy this and show you the badness of past chairs. So sometimes people will do something like this. And the hydrogen isn't angled downward and it's not in an equatorial position. What else? What else have I seen? I've seen people get confused with this carbon and which hydrogen is up and which hydrogen is down. All right, let's talk about chair flipping. To do this, I'm going to I'm going to start with this chair, and again, I'm going to use color. Blue for up carbons. We'll number the atoms of the ring. Sometimes that's really helpful. And then we'll use purple for the down carbons. And let's make this interesting, right? Good luck with that. Let's make this interesting by making one of the substituents not hydrogen. All right? So when we flip the chair, up carbons go up and down carbons go down. Now, your text will often do something like this to indicate flipping of a chair. Go ahead.
You're missing the equatorial substituents on carbon.
Front and the back, yep. Yep, carbon-hydrogen bonds can be assumed to be there, but for now, that was, I don't really like that. Let's try that again. When I was taking this class 20-ish years ago, 22 years ago, Dr. Savage went around the class and we had to draw chairs, and he commented on how ugly the chairs we drew were. So, kind of fun. Which is why I can draw them well now. So when your text will sometimes show chair flipping by drawing the chair in a slightly different orientation. That isn't actually necessarily, that doesn't actually necessarily represent a flipped chair. It's like looking at a chair from this side versus that side. Okay? So it's not wrong to draw it that way, but I've found people get confused. So what I'm going to do when I do a chair flip is I'm going to draw the same basic structure of the chair, but now I'm going to remind myself that after the flip, I'm going to still highlight which carbons are down and which carbons are up, but I'm going to remind myself that after a chair flip, up carbons go down and down carbons go up. My up carbons were 1, 3, and 5. Now my down carbons need to be 1, 3, and 5. And same thing with my formerly down carbons 2, 4, and 6 that are now up. Okay, doing it that way is one way to keep track of what we just said, in that chair flipping involves up carbons go down, down carbons go up. Now we said things that used to be equatorial go axial, things that were axial go equatorial. Now we can't, because a lot of these substituents are hydrogen, we can't really tell. On carbon 3 we can though. This methyl group that used to be down equatorial now has to be down axial. If I keep my up carbons and down carbons straight, and if I keep my numbers straight, then there's no chance for me to get wrong where the methyl group has to be. Right? We could draw in all the other hydrogens if you wanted to. It's not necessary at this point. Maybe I'll just draw in a couple. I just want to illustrate in so doing that what used to be axial, and I'm going to use the same color for the same proton, is now equatorial. And what used to be, I need another color, equatorial, is now axial. But notice, methyl group was down equatorial here. It is now down axial here. Proton was up axial here. It is up equatorial there. Yes?
Is it common to rotate the ring during this process?
Can you?
Because we've rotated it 1 carbon.
So you'll notice that yes, we've moved, we changed which, going around the ring, it looks like we've rotated numbers, and we have. But that is how we're representing that we're literally taking a hold of carbons 1, 3, and 5 and pushing them down, and then 2, 4, and 6 and pulling them up. In other words, this ring has flipped. I just find it most useful to continue to draw the chair in the same way. So it flips, and we move with it a little bit, so we still have the same perspective. Yeah?
Just want to make sure I'm understanding correctly, but the down versus up, that refers to, I guess, the direction that they're going, not whether they're on an up or down carbon.
Exactly. Down versus up for the substituents refers to the direction they're going, not necessarily whether they're on an up carbon or a down carbon. Tricky. Yep. All right. So there's a difference in free energy between these two situations. And the reason for that is that when the methyl group is axial, it starts to bump into those other axial substituents, and we call this a 1,3 diaxial interaction, and sometimes we call that steric hindrance. Now, to give you a picture of what that looks like, we'll go to Spartan, and we're going to add a methyl group. And let's see, download that, clean it up. I want to show you space filling. All right, so in the space filling model, you can see the hydrogens that are pointing directly towards you are the 1, 3, and the 5, I don't know. Those are axial. And the methyl group is at an up equatorial position. I'll turn off space filling so you can see ball and sticks. Now, Spartan actually shows us the two different chair conformations, and it gives us some energies. So this conformation where methyl group is equatorial is about 1.5 kilocalories per mole more stable than the conformation where the methyl group is axial. Now, if you're just looking at the ball and stick models, you can see that the methyl group is axial here, but it may not be clear to you that it is bumping into the other axial groups. So I'm going to show you the space filling model so you can see it. You see how they're basically in contact? Okay? Yeah.
And that's close to what it actually looks like in nature, right?
Sure. I mean, that's a more accurate depiction of the amount of space atoms take up. This is a perfectly fine representation as long as you remember that. So naturally, you would suspect that the more bigger groups you put on the ring, the worse it might be to have something axial versus equatorial. And the other thing maybe some of you've noticed is that this is not necessarily a perfect chair. The carbon-carbon bond involving the methyl group here is not perfectly axial, it's leaning a little bit. And it's leaning a little bit away from those other axial substituents to avoid steric problems. So we can alter our sketch a little bit. Let's use, say, isopropyl, 2 carbons. Ooh, and now it's giving us things to do with different conformations for the groups that are not on the ring. Here is an equatorial conformation. You've got this 3 carbon group, and notice that it can sort of get out of the way and be equatorial without a huge amount of problems. If we change the conformation, let's see. No, that's not what we want. All right, so here is the other chair conformation where that isopropyl group is axial. You can again see that it's leaning, and the reason it's leaning is because those groups are bumping into the other groups. We can make this even worse. Ah, the humanity. By making it a tert butyl group, tertiary butyl group. Notice now, actually, man, I wanted to show you the difference in stability. No, don't. So notice that versus our equatorial conformation, our axial conformation is now, okay. This is actually also an axial conformation. I don't know if you noticed this one, but this was the one where one of the methyl groups was pointed on the isopropyl ring, was pointed directly at the others. there's a better way. You can actually rotate that isopropyl group so it's the hydrogen pointing towards the others, and that looks like it fits better. It's about 1.7 kilocalories per mole higher than the equatorial. Now I want to show you the tert-butyl. T-butyl, tert-butyl, either way. So notice the difference between axial versus, and it actually doesn't, it actually doesn't even want to go equatorial. Like, it's chosen to do something wacky to the ring instead. I'm getting this totally backwards. Let me back up. Try again. The T-butyl group being large is constrained to the equatorial position. The ring does not want to put it at an axial position. And whatever the ring chooses is now even distorting from a chair in order to avoid having the T-butyl group be axial. And the difference between those two conformations is about 5 kilocalories per mole. All right, so we're going to use some of this information. I could say delta G here for this process of going axial to equatorial is about 1-ish kilocalorie per mole, meaning it's uphill, and meaning at equilibrium I would expect to have about 90% of this and about 10% of this. So we'll need to say a little bit more about that next time. We'll also talk about stereochemistry. In the meantime, good luck on the test. The late fee kicks in at 2, so get in before then, and I'll see you Monday.